We present a novel approach to path planning for robotic manipulators through optimization in the latent space of a generative model of robot poses. Path planning consists of finding a sequence of joint angles to move the robot from a start to a go configuration. Traditional approaches suffer from a few issues. First, their planning time scales superlinearly as the complexity of the scene increases. Optimization-based planners are usually not flexible enough to handle constraints that cannot be directly expressed in joint space. Sampling-based planners, on the other hand, struggle to find solutions in scenarios where constraints render only a small volume of configuration space feasible. To address the previously mentioned issues, our idea is to first learn a latent representation of valid robot states. We then learn high-level performance predictors acting on this latent space as well as environment information to guide optimization in latent space. Performing this optimization iteratively produces a sequence of latent values that translates to a joint space path, satisfying the constraints. We learn latent representation of robot state through a variational autoencoder. Our model takes as input the joint configuration and its corresponding end effector position, encodes them to a latent state Z, and then decodes it back. Given a target position, the end effector position of the VAE output is used to compute the distance to the target. Inspired by two recent works using generative models for planning-like tasks, Imagine That and First Steps, paths for target reaching are produced through the iterative use of activation maximization. In other words, we iteratively backpropagate the gradient of the target loss to the latent space. A planned path is produced by decoding a sequence of latent values and taking the joint configuration of the VAE output. Note that our approach does not assume access to the forward kinematics relationship. Thus, we do not take joint configurations of the VAE output to compute the target loss. Without modification, AM, short for activation maximization, may often drive the latent values into parts of the latent space that have not been seen during training. Decoding these latent representations can lead to poor joint configuration and effector position pairs that are inconsistent with the desired kinematics. To encourage the optimization to traverse regions in which the model is well defined, we introduce an additional loss term to the AM objective, consisting of the likelihood of the current latent representation under its prior. Finally, to avoid obstacles, a collision classifier, taking as input the concatenation of latent value Z and obstacle information O, is trained using a binary cross entropy loss while the VAE weights remain frozen. When performing AM in the case of obstacle avoidance, we add an obstacle loss term from binary cross entropy loss to the AM loss. Our approach handles multiple obstacles by simply taking the sum of individual obstacle losses. To gain a better understanding of the importance of prior loss, we plot the reaching success rate versus distance threshold to the target, evaluated on 1,000 scenarios. We found that adding the prior loss in the AM objective function significantly improves reaching success rate. Also, within a distance threshold of 5 mm, we achieve over 90% reaching success. Qualitatively, in the case of no prior loss, one of the joints reaches its joint limit and the robot fails to reach the target, whereas in the case of adding the prior loss, the robot successfully reaches the target. Here we show a side-by-side comparison to demonstrate that the obstacle loss is critical in avoiding obstacles. In this work, we compare our latent space path planning approach with 7 other baselines: RRT Connect, LBKPs, RRT star, Lazy PRM star, FMT star, BitStar, and Chomp. Please refer to the paper for quantitative results. In our one obstacle example, RRT Connect and LBKPs are quick in planning, but found suboptimal paths in terms of path length. Like ours, Chomp is an optimization-based approach. It performs similarly in terms of success rate, but underperforms in path length and planning time. Our approach found a smooth and near optimal path. Similarly, in the case of 3 obstacles, our latent space path planning algorithm planned a smooth and short path. Finally, our latent space path planning approach has been successfully deployed on a real panda arm, as shown in this video. Our approach operates in state space and therefore trivially transfers to the real world. In conclusion, we present a novel approach to path planning for robot manipulation that learns a latent representation of robot states and uses constraint optimization to produce joint space paths to reach end effector goals. In addition to the goal and obstacle losses, we introduce a novel prior loss to encourage the model to stay near the training distribution of robot configurations. In doing so, we bypass the traditional computational challenges while achieving commensurate performance in terms of reaching success, planning time, and path length. Thanks for watching.